Welcome to the course Business Analytics and Data Mining Modeling using R. So in the previous few lectures we have been discussing multiple linear regression, and in the last lecture we were discussing the regression results that we had produced. So let's start with the same exercise. These are the results that we were discussing in the previous lecture. So we stopped at this point when we were comparing the performance of the model that we had built on training partition and testing partition. So we were discussing that the importance of the sample size. However, the point to be understood is that the model that we have just built is performing quite well over the test partition as well. However, this has to be confirmed with a larger sample size. Now a few more things that we can do about our model and to understand the results of our model. For example, the box plot of residuals. So box plot of residuals also in a way gives us some useful information about the model. So let's look at this. Let's create a box plot for residuals. So range is this minus 2.27 to 3.31, and you can see this box plot. The first argument is on residuals, which we have already previously computed as we saw in the previous lecture. The titles and the labeling for y-axis is also given appropriately. The limit that we already have is the range is going to fall within this particular range. So let's execute this line and get the bar plot. So this is the bar plot that we have. So this seems to be a bit more compacted. So main reason being the range is slightly on the wider side, and that is why in every plot that we have been generating, we always focused on the limits. So let's change the limits appropriately. Let's make it 3 and this one as 4, and then we would have a much regular box plot, not the compressed one. You can see the change in results and a much better box plot in this case. So as we have discussed in the when we were discussing visualization techniques, that the box plot contains some important information for us. For example, in this case we can see that different values, the few outliers that are there, right, and the majority of values which are represented by the first quartile and third quartile and the range where they are lying, right. So majority of value, they seem to be this minus 1 to something more than 0, right. So this range, right. So this is the range for box plot, and from the look of it, it looks to be right skewed. So we can easily find that out. There is another important function that we are going to discuss. This is quantile function. So if you want to compute the values for different quantiles, so this is how you can do this. So for example, we are interested in first quantile and third quartile, reason being that the box that we generally generate using box plot, that indicates that the majority of values are lying between first quantile and third quantile. Majority means 50%, about 50% or even more or values are lying in between these two plots. So let's compute the these quantiles. You can see the number. So if we have to compute the range for these, so the 50% values as indicated by these quantiles are lying between approximately between minus 0.8 to 0.4. So that is the range where more than 50% or approximately 50% of the values are lying. Now as we were talking about the skewness, so we can do the same by computing mean and median value. So in this case we can see the mean value is slightly on the higher side than median value, and we can also see the some outliers there. So therefore this particular residuals, they seem to be following normal distribution, which is right skewed. So we can check this again by plotting a histogram. So now what we are going to do is we are going to plot histogram on the outcome variable. So this is the price, outcome variable is the price. So let's plot this, and you can see the skewness. you can see the skewness, that this seems to be clearly right skewed distribution, right, normal distribution. So we can again confirm the same thing using few different plots. For example, one popular plot that is generally used is normal probability plot. So we have QQ norm function to generate the same. So we are going to use this. This is the so we are applying QQ norm on outcome variable df price, and this is the plot that we get. We want to have a reference line on which we can compare whether the plot is whether following normal distribution or not. So this is the line. So in the normal QQ plot, we see that as we move from left to right on the right part, many observations they start deviating from this reference line that we have just drawn. So that indicating the right skewness, right. For a normal distribution, these points would be distributed along this reference line. If there is some deviation, that indicates the skewness in the plot in the normal distribution. So as you see that we are mainly, when we talk about the distribution, specifically normal distribution, we are mainly interested in residuals and the outcome variable. So in this case, we have checked both. Now generally for our data mining modeling, the outcome variable or the residuals not following the normal distribution is not such a problem, because generally the performance that we how we assess the performance is on using different partitions. So therefore we don't have to, so we get some relaxation from that assumption that we talked about. But if you are dealing in a if you are doing a statistical modeling, so in that case people generally prefer to do some transformation so that their outcome variable of interest, it follows normal distribution. So we are going to do the same. So from the looks of it, we saw that outcome variable, it seems to be rightly skewed. So log transformation would be appropriate for it to for it to make it more a normal distribution. You would see that in a log form, log curve, log function, majority of the value they lie in this smaller range, and then the there is a long range that is taken on the other values which are slightly on the higher side. So therefore log transformation seems to be more suitable to make it look like more normal distribution. So if we plot a histogram, we generate histogram on log of df dollar price, right, then we will get whether we will see that whether we are getting a normal. Now you see this, once we have generated, now this seems to be more of a normal distribution. If we compare this particular plot to previous histogram that we had plotted, this seems to be following normal distribution. In the other plot, there was a clear skewness, right skewness in the plot. Now from the plot, what we understand is now we can use this log transformed value as the outcome variable of interest in our regression model. So let's see this. So we are again going to run one more model. So this is on the transformed value, log transformed value. So you can see in the LM function we have log, and then we are taking log of price, and this is the model is being run on log of price and the set of predictors on the training partition. So let's execute this. So we get the model, and now let's also score using this model. Let's also score the test partition. So you can see that we are again using the predict function, and we are passing on the new model, that is mod 2 in this for this time, because we want to score the test partition using this new model that we have just built. So let's execute this code. So this has been scored. Now we are again going to use this m metric function. So you can see the first argument being the this is for the test partition. So first argument being the outcome variable for the test partition coming from the test partition, and then you can see the values that we have just computed mod test 2, we are taking an exponential of that value, because if you remember that we have done log transformation. So therefore the scores that we would get on test partition, they would be in that scale itself. So therefore we need to bring those values to the normal or regular scales, so that we can done using applying the exponential function on the scored values, and therefore the values would return to the normal scale, and then these values could be used to compute the matrix, because the idea is to compare the performance of this transform model with respect to the previous model that we have, and that too on test partition. So let's compute these values, and you can see the number. Now if we look at the values, you can see that earlier the results, if we look at the RMSE value, it was 1.16, right, for the earlier model, and now it is 1.11, right. So even in this case the error is further reducing. So this might not always be the case, because once you transform, the typical scenario could be that this RMSE value, this error might slightly increase, right. But in this particular instance, the error is even when we run a transform model, when we transform our outcome variable, and then even in that case the model is doing even better. You can see that even the SSE value is lower than the previous value that we had. In this case it is 37, and the previous value was 40 here. So in this case the samples, the partition that we have for after doing log transformation, we are getting even better results. However, the word of caution would be that as I have said in the previous lecture as well, that we are doing this exercise on a small sample size, having just the 75 observations. So therefore the results are not that much reliable. So therefore we have to use a larger sample size, so that the results are comparable in a much broader sense. Now, so this was about the regular regression analysis that we have just done. Now let's move to our next discussion, that is on variable selection. So when we were discussing dimension reduction techniques in our previous modules and lectures, so we talked about the principal component analysis and how it could be used to reduce the dimension. We also discussed that some of the data mining techniques, right, they could also be used to perform the dimension reduction. So now we also talked about at that time that the regression analysis could also be used to perform this, and we also talked about that CART could also be used. So in this right now we are going to discuss how the regression modeling can actually be used to perform variable selection, and that in a way also is for dimension reduction. So generally when we are dealing with large data sets, we also have large number of variables, and from those large number of variables we will have to select the useful predictors for our prediction or classification task. So how do we do that? Because the main idea for our modeling exercises is to select the most useful set of predictors for a given outcome variable of interest. So therefore from those large number of variables, the 20, 50, 100 or even 200 variables that we might have in our data set, how do we identify the most useful set of predictors of 5, 6, 7, 8 to 10 variables for our modeling, right? So variable selection, that using regression models, that could be the one alternative solution to perform this. Now at this point I would like to mention that as explained in the slide also, that selecting all the variables in the model is not recommended. So now because of the computing the softwares that we have, that immediately you might be tempted to have all the models in your all the variables in your model, and then later on selecting and the useful variables from that from those results. So that is not recommended for a number of reasons. For example, data collection issues in future. If you are having many variables in the model, and later on if you are required to rerun the model, and because you would like to compare the performance of the model to the previous model as well, but in future you might not be able to collect the data on all the variables. So as you increase the number of variables in your model, the data collection issues in future might hamper your comparison and the analysis. So therefore you have to bear this thing in mind, that there could be data collection issues if you build your model using all the variables that are available. Now measurement accuracy issues for some variables. Now some of the variables, because generally when we talk about the statistical modeling, generally we are dealing with primary data, as we discussed in the previous lectures. Some of these variables are measured using the survey instrument. Now there are generally many of these variables are perceptual variables also. So there are generally the measurement issues, measurement and the accuracy issues about the data that we collect. So because of that, it is not recommended that whatever data that you have, it is not recommended that you include all the variables in the model. You might choose to eliminate some of the variables which might be having some accuracy related problems, measurement accuracy related problems. Now missing values. If you are having more variables in your model, missing values could complicate the problem much more. If there are more variables in the model, having a missing value in even just one cell might lead to eliminating or removing more number of records, right. So therefore if you have more variables in the model, there are more chances of having missing values in the data set, and then even more chances to remove more number of records, more number of observations or rows from your data set because of the missing values, or depending on the imputation that you have. So usefulness of your model can also be under question. Now the another region is parsimony. So as we have discussed before, we would like to follow the principle of parsimony. So therefore it is always recommended that we try to build a model with as few as predictors and still be able to explain the most of the variability in the outcome variable interest. That is the ideal scenario that we want. So with respect to this principle of parsimony also, we should be building our model on fewer variables, and model building on all the variables is not recommended. Now few more regions, the another one being multicollinearity. So we touched upon multicollinearity in previous lectures as well, and we will do the same again in coming lectures as well. So what is multicollinearity? So this is briefly this is about two or more predictors sharing the same linear relationship with the outcome variable of interest, right. So as we have talked about, that one of the assumptions in regression analysis is that cases should be independent, right. Otherwise that is going to might produce the or might affect the estimates of reliability of the regression coefficient, those estimates, right. So if those cases should be independent. The same applies on the variables also, the column side. So on the rows side also the cases should be independent. On the column side, that is the variables that we are talking about, we say that multicollinearity should not be there. This is even more applicable to regression analysis and other statistical techniques. So many predictors having the same relationship with the outcome variables in a way is very similar to having two dependent rows. So we don't want that in our data. So we would like to eliminate the multicollinearity issues if there are two predictors which are having the same relationship with the outcome variable, and if we include both of them in the model, the results that we might get would be dominated by the information that is there in these two variables, and therefore our model would render useless. So therefore we would like to eliminate the multicollinearity issues, and if we are including more variables in our model, there are more chances for multicollinearity to appear in our model. There are more variables, so of course some few variables might be highly correlated. There are good chances of few variables being highly correlated, and therefore multicollinearity could be there in the model. So therefore for this reason also it is recommended that we should do our modeling with fewer variables. Now let us move to the next point, that is sample size issues. So few rule of thumb for sample sizes we have been discussing before. For example, this one particular is that number of observation that we have should be greater than 5 times of number of predictors plus 2 value, right. So if there are if there are p predictors, so we would like to have number of observation more than 5 into p plus 2, right. So if we have the main logic being, if we have more number of predictors, our requirement for having a number of observation will also go up. So if we have 100 variables in our model and we want to include all of them in our model, so that would increase the number of predictors, that is p value. So therefore our requirement for the number of observations would also go up. So sample size issues could also be encountered if we have more predictors in our model. Now few other things would also be there. For example, variance of predictions that we do after modeling might increase due to inclusion of predictors which are uncorrelated with the outcome variable. So if we are having more number of variables in the model, so there are there are more chances for including some uncorrelated variables, some predictors which are uncorrelated with the outcome variable, and therefore they will increase the variance of predictions. So that is avoidable. Now another issues that we might face is the average error of prediction. So average error of prediction might increase if we exclude some of the predictors which are correlated with the outcome variables. So as I have said, for us when we do any kind of analytics, whether it is based on data mining or whether it is based on statistical techniques, we are always looking to build model, we are always looking to predict values or classes in different tasks that we do. So in all those situations, if there are variables that we are analyzing, if they are correlated only, then we would be able to do our job. But as we discussed, if the variables are highly correlated, then of course we would like to avoid that situation. Similarly, if the variables are not correlated at all, we would like to avoid that situation as well. So therefore we are interested in the mid range where the variables are slightly correlated, less than moderately correlated, and therefore our average error of prediction that could be kept on check. So if we exclude predictors which are correlated with the outcome variables, our average error of prediction will go up. So therefore we have to we have to balance on both sides. We would not like to have highly correlated variables, because that would again those variables might dominate the results, as we discussed multicollinearity issues. Similarly, if there are uncorrelated variables, they will increase the variance, which is not desirable. So we would not like to have those uncorrelated variables as well. So we would like to have we also have to make sure that the variables which are correlated, that are in the mid range, low or mid range, having low or mid range correlation, we would like to have those predictors in our model. This brings us to another concept related to the same discussion, that is bias variance trade-off. So bias variance trade-off is important, especially when you try to include many variables. Then what is going to happen is your variance will be negatively impacted. When you have low number of variables, your bias, that is the average error, that is going to be negatively impacted. So we have to balance between bias and variance. So for example, so this scenario sometimes is also referred as too few versus too many predictors, whether we should have too few or too many predictors. So both these situations are avoided, should be avoided. We should have a balanced approach, bias variance trade-off. That balance has to be maintained. So if we have few predictors, that is going to be leading to higher bias, that is as we discussed, higher average error, and therefore lower variance. So the lower variance is desirable, but then you would also would not like to have the higher bias. So therefore that is the trade-off that we need to do, that we need to perform. So what could be done? So we can drop variables with coefficient with are less than standard deviation of noise, and with moderate or high correlation with other variables. So as we discussed that if our variables, our predictors, they are moderately or highly correlated with other variables, right, and they are also having coefficient which is less than standard deviation of noise, then probably they are good candidates for dropping. So as we have discussed when we were discussing the regression results, so some of the variables which are having coefficient value less than standard deviation of noise and also being correlated, highly correlated or moderately or highly correlated with the other variables, so they could be dropped, and if this is done, then we will achieve lower variance which is desirable. So sometimes we accept even a bit more bias to achieve lower variance, because variance is more desirable for our modeling exercises. So sometimes we accept even more bias to achieve lower variance. Therefore most of the recommendations that you would see, they are generally driven towards variance, achieving lower variance. Now this brings to our next discussion, that is steps to reduce the number of predictors that we have been discussing. So what could be the steps that we can take? So domain knowledge is one. So using your domain knowledge, having done some work in the same area, having some knowledge about the different relationship, different phenomena, constructs, variables, that will give you, that will give you some more expertise to find out the predictors which are more sensible with respect to the task that we had, whether it is prediction or classification or even the statistical modeling. So domain knowledge is always going to help you in terms of identifying which variables are going to be useful for the modeling exercise that you are performing. So the first reduction you can do based on your domain knowledge. Now practical regions could be the another approach. So most of the discussion that we did just before, all of them would be applicable under practical regions. So discussion in the previous slide that we had done for variable selection, why we should have fewer variables. So all these points, they would also be they will also give us some direction, some practical regions that we talked about. For example, the first one that we discussed, that data collection issues and missing values, right. So all those points provide us some practical regions to reduce the number of predictors. Few other things that we have discussed in previous modules, also summary statistics and graph that we have done in our visualization techniques lectures, right. So this could also be done. So in this particular topic, multiple linear regression, our focus is on statistical methods and to also exploit the computational power that we have nowadays. So the two approaches are common or popular: exhaustive search, that is to search all possible combination of predictors and find out the best subset which is fitting the data. So that is one approach. This is more like brute force approach. So first one is exhaustive search. It's like a brute force approach where we are checking all possible combination of predictors, and we would like to identify the subset of a subset of those predictors which is giving the best fit to the data. Now the second approach is partial iterative search. This is more of algorithm driven, more optimized approaches, right. So we are going to discuss these two approaches in coming lectures. So first let us start with exhaustive search and few points, and then we will continue on the same in the next lecture. So exhaustive search, large number of subsets we are going to examine, because we are going to check all possible combinations. criteria that we generally use to compare models. So, different subsets and comparison between those models, subset models would be generally be based on adjusted R square and R square and mellow CP that we are going to discuss in coming lectures. So, we will stop at this point, and our next discussion is going to be around the exhaustive search and the criteria that are used to perform that, and then we will also do an exercise in RStudio to understand how this is done. We will stop here. Thank you.